So for the past couple months, I have been spending some time reflecting on my math degree and also what I wanted to know before I started my math degree. And in particular, the one question that comes to mind a ton is what comes after calculus? It was something that I always wondered about. I wasn't really sure. Everything that I did independently outside of school was up until calculus and then like a little bit of differential equations, and then everything I did in school was just up through like AP, BC Calc or whatever. So I thought today I would go through and give a brief summary of each of the 22 math courses I took in undergrad. And yes, I did say 22. For most people right now, you're wondering, why would someone ever do this to themselves? But the real kicker here is that I planned on taking 27. 5 of them were cut because I decided to take a term off to help out my family when there was some stuff going on. So, I'm gonna go grab the books. And yes, I kept all of the books. Also, since this is going to be a longer video, I'm going to put the shameless plug at the beginning. If you are excited about this video or want to see more math content, you can subscribe to my channel and give this video a thumbs up to let me know that I should keep doing this. So, what comes after calculus? First off, a little disclaimer here, even though I only took up to BC Calc, I actually didn't take calculus in college. I ended up self-studying this guy for all of the content that I needed for multivariable calc or Calc 3. And that's sort of how I got through that requirement. I just came in and was like, I did all this work over the summer and I know my stuff. Can I please not take this class? And they said yes, which was great. So I actually didn't take this, and since this is what comes after calc, I don't want to spend any more time on a computational calculus course. So we're gonna just skip this one. The first mathematics course that I took in undergrad was actually a linear algebra course. If it will focus. Will it focus? Is it too bright in here? It's probably too bright. Is that okay? Yes, it's a linear algebra course. You'll see it on the chalkboard. So this linear algebra class was primarily computation based. We learned a lot about the different matrix operations, and we did some loose computational proofs that were not super logic heavy. After moving on from all the matrix computation basics, we then started to talk about linear transformations and different mathematical objects and definitions related to linear transformations, like images and kernels, along with linear independence. We covered the rank nullity theorem, isomorphisms, the Grand-Schmidt process, and orthonormal factorizations of matrices. I think the last thing we covered was eigenvalues and eigenvectors, and then some diagonalization and diagonalizability, which is the best math word, mind you. That aside, next thing was introduction to mathematical structures. This class was a general introduction to proof methods and logic. We started out with logic and Boolean algebra and talked about things like tautologies and Russell's paradox, and then continued on to various proof methods. Direct, contrapositive, contradiction, various flavors of induction, and case analysis were included here. In order to introduce these things, we spent a lot of time with sets and different mathematical structures related to sets, like functions and relations, equivalence relations, and equivalence classes. Modular arithmetic was brought up as well. We also talked a lot about cardinality and the Cantor-Schroeder-Bernstein theorem, and then since my professor was a topologist, we ended the course on the proof of the four-color theorem. Looking back, I'm not entirely sure that we covered the four-color theorem just because my professor was a topologist and it was interesting to topology, or if it was just a good way to introduce computer-assisted proof methods, or proofing, because the four-color theorem is known as the first computer-based proof, or computer-assisted proof. The next class I took was called Differential Forms and Vector Calculus, which was based on this book, which just looks like white paper right now because of how bright my lights are. But it was this really cool class that I initially thought was going to be terrible, and I took it because I wanted to take at least one math class each term, and this was the only one that I could actually register for during this term. And to my surprise, it was amazing because we spent the entire class talking about the dx on the end of the integral, essentially, or talking about differential forms. And so here we go. So as I mentioned just a second ago, we spent a lot of time on the dx on the end of the integral, which is cool because basically no one had ever explained to me what that thing is, where it comes from, why it's important, what mathematically it is, how to rigorously define it, any of the stuff that someone should do with a mathematical object. We talked about differential forms, discussed anti-commutativity, went over the Hodge-star operator, generalized divergence, gradient, and curl for n-dimensional space. And we also proved Fubini's theorem, which is the one about being able to switch the integrals. We ended the course with a proof of the generalized Stokes theorem for n space. There was a lot of summation accounting going on here as well, but it was still super interesting. Okay, number 4, real analysis 1. This class started out with the professor telling us that it would be the most difficult class in our undergraduate career, but I'll tell you why later, but he was 100% wrong. There were like 2 other classes that I would say were harder than this one. This class focused on the rigorization of calculus and set theory. So we spent a lot of time being very, very careful and proving pretty much everything you take for granted in a computational calculus course. Stuff about sequences and series, and then proving that certain convergence tests actually work. We also went over limits, continuity, differentiability, and ended on defining the Riemann integral rigorously. And we did most of the stuff using epsilons and deltas. Number 5 was a little bit atypical for a math course. I was a huge language nerd at the beginning of my mathematics career. And so I really wanted to be able to read math in one of the languages that I was taking. So I took Chinese and Greek in college, and also had studied modern Greek outside of college as well. So it just made the most sense to go with Greek because Euclid is a dude. Now, mind you, this is not the copy of the text that I used, but I spent a term reading Euclid's Elements in the original, which was pretty cool. I'm not going to throw this book because this book was expensive, and also I just don't want to tear the binding any more than it is. So we're just going to place it on the board. Just give me a second. So this class was way more relaxing than any other math course I had taken up till this point. It was still proof-based Euclidean geometry, but I was graded on my ability to explain and reason the proofs based on the Greek. I got to read through some constructions and the proof of the Pythagorean theorem in Greek as well. Not super important, but kind of cool. I learned that the ancient Greek equivalent of QED, so QED is Latin. The Greek equivalent of that is Oper Eda Dexai, which is, I don't know, that's fun, but this was the closest thing that I got to a geometries course before leaving undergrad. All right, number 6, abstract algebra. So my first thought when taking this course was that, 1, I needed to take higher level courses, so I needed to take this class, but also I felt like I was going backwards because the course had algebra in the name. This was pretty far from the truth. It would end up being pretty new. We went over a plethora of mathematical objects related to 3 core algebraic structures, groups, rings, and fields. And at the end of the course, I was actually pretty happy that I took the course. It's a very cool subject, and it's something that is very enjoyable to study. It's like doing a lot of number puzzles for fun. It's wonderful. It was still a pretty challenging course since up until that point, I had been pretty focused on the analysis side of things. But it was a really cool class. Number 7 is ordinary differential equations. Or at least, yes, it was called this. We'll get into why that's weird in a second here. So this class was hard for me to get through just because I was taking 8 and 9. Which we'll get to in a second, and this one was much slower paced than the other 2 courses I was taking while taking this course. In reality, this course should have been called Harmonic Oscillators, and it wasn't the most positive introduction to applied mathematics, for me at least, because we pretty much spent the entire time understanding the universal oscillator equation, which is this dude. I just definitely wished we did more in this class, and it was a lot slower compared to the next two classes that I'm going to talk about, which I actually took during the same time as this one. So number 8 was a little bit different because this was the first course where there wasn't actually like a assigned reading that we needed to do. Instead, we got these like lovely handwritten notes from our professor. And this was this was definitely more difficult than Real Analysis 1 was. This was terrifying, to be quite honest, but we got to prove some really cool stuff. So here we spent most of our time with field extensions and different constructions that involved fields. We went over an algebraic construction of the complex numbers, and then to my surprise, we talked about Euclidean constructibility theorems. So in short, proving that you can or cannot construct certain geometric objects with just a compass and straight edge, which actually made my independent study reading Euclid's Elements in the original super helpful. Later on in this course, we talked about towers, constructible numbers, and Galois groups. Symmetric polynomials, splitting fields, separability, the fundamental theorem of Galois theory, the Jordan-Holder theorem, solvability, and then we went over some irreducible quintics. So in short, we covered a ton. I can't really get into the specifics of most of it right now, but my mind was fried by the end of that class. So number 9 was another course that I took during the previous two, and that was in complex analysis, which also, I'm not going to throw this book because it's literally falling apart. Sad day. I just like to read the beginning of this because it's really cool. And it helps me remember all the definitions that go with complex functions. Anyway, I'm just gonna take a second. Here we talked about different types of functions of a complex variable. We also focused a lot on different integration techniques. The weirdest one that I remember was keyhole integration, which had you integrate along a contour like this one. My professor was pretty ambitious, and we covered a lot of conformal mapping theory that the course usually didn't cover, and we ended on the proof of one of the coolest theorems I have ever had the joy of learning about, called the Riemann mapping theorem. At some point, we also proved the fundamental theorem of algebra, and it's weird that the fundamental theorem of algebra is a theorem from complex analysis. It's just weird. Next, we've got number theory, or elementary theory of numbers, or whatever you want to call a introductory course to number theory. So I came into this course a little bit flustered since it occurred right after my term off, and I was a bit confused as to what I would use it for down the line, since it was the only course in number theory offered at my school. We talked about things like Fermat's little theorem, Jacobi and Legendre symbols, along with quadratic reciprocity, arithmetic functions, cyclotomic polynomials, partitions of an integer, primes, and the Chinese remainder theorem were all other things that we went through as well. Number 11. Real Analysis 2, and you can tell that the books are getting smaller. That doesn't necessarily mean the classes are getting easier, but that's just something that's cool about math, is that the higher you go, the smaller the books get. So this was a introduction to measure theory course. So we spent a lot of time on defining outer measures and measures, what it meant to be a measurable set and a measurable function, and then leading into things like Lebesgue integration and what it means to integrate over a measurable set. There were a handful of really important theorems that we proved in this class too. The Lebesgue-dominated convergence theorem, Fatou's lemma, and the monotone convergence theorem were all covered. We also talked about LP spaces and Holder's inequality as well. My professor for this course had research interests in fractal geometry, so I got to do my final project learning about the Hausdorff measure and Hausdorff dimension, which was my first introduction to information content valuations, which closely relates to the mathematical stuff that I'm interested in today. So number 12 was by far the hardest course I took in undergrad, and it was on the theory of elliptic curves, which this book stresses me out. Quite frankly, it is one behemoth of a textbook for an undergrad textbook. But yeah, I'm just gonna... This was the closest thing I got to a differential geometry course in undergrad, but If you want to call it a differential geometry course, that would be wrong because it was highly specific and we focused on one type of non-singular curve. And you think that would make the class easier? It made it worse. We didn't even focus on just one type of curve that was non-singular. We focused on one form of those non-singular curves called the Weierstrass normal form. And it was a computational terror of a course. We did a lot of math on these curves and defining a group and an algebraic structure between points on these curves and figuring out computationally how to calculate those additions was pretty intense, especially when you're doing it by hand. We talked about existence and structure theorems for points of finite order on an elliptic curve, like the Nagel-Lutz theorem and the abridged Mordel's theorem, which was essentially that there was a finitely generated group associated with the rational points on a curve, which is totally freaking crazy. But anyway, continuing. We also went over height and the corresponding descent theorem that can be used to perform proofs by descent. At the end of the course, we talked about elliptic curve cryptography and factorization, which fed into the earlier computations that we did in the class, along with briefly introducing the monster of a proof behind Fermat's last theorem. Okay, so next up we have probability, which was basically a break from all of this hard stuff that I did. So this course was a generic, you've taken calculus, now let's do something with it kind of probability course. We started with the combinatorial notion of probability and then moved on to continuous probability and different equations and theorems that were helpful in probability theory, like Bayes' formula. There was also a lot of coding in R, which is a statistical computing program. And we have number 14, which was advanced linear algebra. This was the first course that actually did not have a set textbook. I just have this textbook because it has a lot of the stuff that we did in that class. But instead of having a textbook dedicated to it, it was just a reference list of books that we had to check out from the library every once in a while. Before taking this class, I thought it would just be matrices on steroids, and that's why I avoided it for so long. But it was more about developing the more general idea of vector spaces and being very proof-oriented about linear algebra, which makes for some mind-bending accounting of the different elements' location in an abstract matrix. We ended the class with the Cayley-Hamilton theorem and Jordan canonical form of a square matrix, which were both pretty satisfying results. Okay, so I'm going to do numbers 15, 16, and 17 all at the same time because they, in some way, shape, or form, all originate from this textbook, which was what basically kicked me off in my senior comprehensive project, which is basically the thing that determined if I graduated or not, and my independent research, which took place over 2 terms, and we did slightly different things each term with that. Yes. So my senior comprehensive project was a very combinatorial thing. We spent a lot of time doing counting and whatnot, but the focus was on topological entropy of 2-dimensional symbolic spaces. And so the reason that we were counting all the time is because that topological entropy problem in 2 dimensions reduces down to a very difficult counting problem. As the comprehensive project was a group research project, we had a little bit more freedom to be creative with the mathematics we were doing. And so we spent our time formulating an analogous valuation of entropy, or like an entropy-like calculation that we could use on the corresponding tiling space. We weren't able to prove that it was the same as topological entropy, but it had some of the same flavor of calculation, and so it was providing similar information, and we were able to easily get upper and lower bounds on that, which was really cool. For 16 and 17, those were listed on my transcript as Symbolic Dynamics 1 and Symbolic Dynamics 2. These courses were my independent research courses. In contrast to my comprehensive project, these courses were heavily focused on 1-dimensional symbolic dynamics and generating special spaces in 1-dimensional symbolic dynamics. So my focus here the first term was to understand how substitution dynamics work and how substitutions can be used to generate symbolic dynamic spaces in 1 dimension. So the thing about substitution spaces is that their topological entropy is 0. So what I started to think about was, instead of having one substitution generate your space, what if you had a symbolic space on substitutions that was used to generate a symbolic space on an alphabet, and would that do any better? That was a really cool project because I ended up getting to present a lot of my work at JMM, and I've done a video or two related to symbolic dynamics here on the channel too, so there's that as well. Number 18 is Topology. This was not the book that was assigned for the class, because we didn't have one assigned for the class. It was just notes, but this was where my professor got all of his notes, and I assume a lot of the stuff that he lectured about corresponded directly to what was in here. Yeah, Moncrief will get you somewhere. So, just gonna, come on, throw the book, Nathan, throw the book. I don't wanna throw the book. So Topology was a very different course in comparison to pretty much everything that I had taken before. I had a good context due to my background in analysis, but topology is a very general subject. We talked about different topologies and their properties, and then we worked on developing the ideas to prove a topological classification theorem for three-dimensional surfaces. We talked a lot about fundamental groups of a topological space too, which was the first contact I had with anything that represented anything about category theory. And my final project here took on knot theory and knot polynomials and how they can be used to generate a knot invariant. Number 19, we almost done. It's gonna be great. Number 19 was this guy, an introduction to computability and complexity theory, which was technically a theoretical computer science class, but everything was proved like it was a math class, which is why I really enjoyed it. And it also is just really cool. So here we pretty much approached everything with a mathematical proof, which made this class super cool. And we talked about how one could generate different languages using different abstract machines like deterministic finite state automaton, context-free grammars, and Turing machines. I recently did a video that relates to that stuff too, which I'll put up in the corner as well if you're interested. Number 20 is stats, and we can skip this one because I just brought it up because I really want to throw the book. It was just an extension of probability. And then 21 was fractal geometry. Again, this course was like an assorted reading course. This is just a book that I have that I got after the fact because I thought it was very related to the things that we studied, so I could have a book that goes over that material. Yes, I'm going to throw it now, even though I don't want to, because it's a really nice book. Anyway, so fractal geometry was a class on the rigorous mathematics behind all of those super cool, mesmerizing pictures of fractals. We focused primarily on iterated function systems, which is one of the mathematical objects that can be used to generate a fractal, and different dimension flavors like Hausdorff and box dimension 2. All right, last one, number 22 was Fourier series. This book stresses me out too. This book. So this class made me question if sleep was possible, and apparently that's how my life is going now too, so it prepared me for the real world. We covered partial differential equations and just general Fourier analysis and Fourier transformations. I was definitely not the happiest camper in this class because it didn't feel as rigorous as some of the other classes I had taken during my time in undergrad, but that is just how this class went. It was another applied mathematics course, and it was very computation heavy. Anyhow, that was all of the courses that I took during my time in undergrad. The two that I didn't get to take that I wanted to take were combinatorics and differential geometry, and then the three other ones that I had slated were an abstract algebra course in representation theory, and then 2 courses in graph theory. And all 5 of those sort of were slated for that term where I decided to take it off and help out with some family stuff. So yes, that is what comes after calculus. If you enjoyed this video, give it a thumbs up. I have more mathematical content all over my channel. And you've probably seen some of the cards pop up as well, so you can subscribe and like for more of that stuff. And yeah, this was a very long video, but I did it. I did the thing. So yeah. I'm Nathan, this is Chalk, and I will see you next time.